So here I give a little bit of first introduction about the measurement campaign we are actually conducting the BRE. Just following the description by Ben, so we established set up the measurement test bed to measure all different results at the BRE lab. And okay, this measurement we need to first to measure the event coverage. And the event coverage will be measured first VOC, so based on the threshold for EVN 8%, and also for the millimeter wave, also we have 8% EVN, and also for the EMF measurement for power measurement, so emission power from the VOC and the millimeter wave, also regards the location power measurement for the VOC and the millimeter wave. And so the whole system is set up by the RAM, 5G RAM. So this is based on the RunEL base station and DRAM plus distributor remote radio light head. And the receiver will be conducted at Viavi test UE. So we have all the necessary measurement, including the EVN and the power, and also the power distribution or event distribution. And also we can have the CRC decoding and also the application data as well. So this is the layout of the BIA lab. So eventually we will actually, if you, so this is actually the measurement campaign. This is like a living room. And this is like a lobby, an intern lobby. This is a kitchen. So we installed the VOC and the mid-wave over here. And this is like a open plan, like a greenhouse, open plan greenhouse. So for VOC, they have A, B, C, D. We named A, B, C, D with 4 different lights and all can transmit vertically down. And the receiver, we will be moving along the track. So this track already measured with a fixed distance. And ground level and also the table level. So table roughly 70 centimeters above the ground level. So now this is the user equipment. So we, all the necessary decoding and also the measurement and also the application data will be further processing inside the server and the print out display the TV, smart TV over here. So all this system will be fully calibrated. So we first do the calibration for the power and also the connection and also the power measurements and also for the distance. So this is for the whole setup, the initial setup, and also the signal level at individual stages, and also for the base station, we calibrate the base station towards to the mid wave, and also towards to the VOC. They have a different power level, and also working for different bandwidths. And this is we mounted with VOC and the mid wave together because they are working at a different band, and so they can, without interference, you can transmit at the same time. So this is a VOC light. So this is a VOC dedicated for the sport night, with sport night and also communication and the lighting together. And this is housing for the millimeter wave, and this will be changing vertical down 30 degree or 40 degree towards the compared to vertical horizontal direction. And this home antenna that can used for the millimeter wave, working for the 40 hertz, 40 gigahertz. And at the receive side, similar, we also with a different angle, as I just mentioned in the slides, we take it for this is the VOC of a millimeter wave with angling and also VOC with angling. So this we can measure what is the angle we used at the receiver side to take the measurement. So this is this is a Viavi UE. So from the Viavi UE, we can actually, this is GUI. So from this GUI, also they can support the export the measurement results. So any results you can export the file for the further processing. So this is average EVN to measure for over 1 minute. And this EVN distribution or constellation, and also block error rate, and also the throughput, and also CRC check. Besides this, also all the application data you can take out to send to the like the data payload, so to the display like a video streaming data. So this supports the PDSH and also PBSH, all the control channel and the data channel measurement. So this is for the coverage. Normally, for the EVM measurement, we have a different several coverage threshold. For the section 4 CRAN, this we use for millimeter wave with 80%, and for the VOC we use QPSK. So this threshold is 12%. So the first measurement result we have, this is for the nightling VOC and also the without angling. So in this scenario, the VOC and the night, transmitter night and the receive night all horizontally point from each other. So the transmitter vertical down and the receiver vertical up. So we can see you have a coverage threshold 8%, roughly 8% here. So A, B, C, D, you can see 4 different nights. We have a 4 different transmission coverage region. So now if we change the angling, we can see the for individual nights, we have a improve the coverage for the blue region. So blue region roughly is 8% EVN range. And also the ABCD, there's two different nights. We have a different EVN performance. Depends on depends on how you do the calibration of your receiver and all the transmitter nights. So this is the layout for the positioning. So actually, the individual, the red mark here, we use as a reference point for the positioning. So all the measurement we taking at the fixed location, and we do the power measurement. For the power measurement, we receive the power from the decoded data, and we take the power average over the subcarrier, and then send this data back to the server for further processing for the for the location estimation. So if you consider blue points is the location we test, we take the power measurement. And the red point is we average over the, we estimate the location. So averaging location, we can achieve the less than 10 centimeters, 8% of the position error will be less than 10 centimeters. And also this power measurement could be enhanced by the more calibration results will be better, more accurate results can be achieved. And also this is for the millimeter wave. For the millimeter wave, we also do the several configurations. So this is the configuration where first we used the without angling. So that means the transmitter will be vertical down, and also the transmitter receiver vertical up. So this is, so in this case we can see you have a table underneath the receiver. So some reflection is already being shielded by the table. So the ranging will be slightly rough. So 8% will be rough this range. Now, if we with the table angled, we can see here it's much improved the performance of the EVN coverage. So in this case, we can see the huge the angling do affect a lot of receiver performance by the reflection and also the direct link of your millimeter wave module. And this is a without table. So now if you configure actually this very interested. This figure with this figure. This is a under on top of the table. This is direct on the floor. So this part actually is worse. So this is because you have a lot of reflection direct on the floor. And if you put the signal over floor, this reflection will destroy your signal. And this will be improve your signal because your table will share a lot of reflection and this reflection will damage your channel estimation at the receiver side. Similar, now if you point angling, actually, and this angling will improve the multipass effect. So you can improve the angling, but you still have this pattern inside your antenna at a central point, even with angling. So this is 30 degree. From 30 degree, you can see this is the positioning over here. So 30 degree, you can see the coverage will be slightly along this range. And you have a lot of flexion over here. So this is some table, and also they have the TV sets over around here, so reflection from TV down to ground. And this is a vertical, so 30 degree from the vertical and without angle and with angle. If a raised angle, this will remove a lot of reflection, so much better than the without angle. So you have this reflection, so this will be much better in this range. So similar, 40 degree will be, with angling will be even better. So for the blue area, will be much. So in this case, for the 40 degree, that means you transmit the signal will always towards the more angling towards the down to ground. And so this is a 0.7 meter. So in this case, we put this receiver at the table. So the table will shield a lot of reflection. So the multipass will be slightly better. In this case, the channel estimation window will be handled. We can handle the equalizer enough for the local reflection from the ground signal. So all the measurement also we test with a different throughput. So we running at the TV video streaming for the millimeter wave and also for the VOC system. The VOC system will run at 10 megahertz. So the throughput 42 megabit per second. And for the millimeter wave, because we only use one user, so 310 megabit per second per user. And for the overall, we can achieve, so for 4 nights all on and working at 400 megahertz, we can achieve roughly 1 gigabit per second per one remote radio line head controller. And also this remote radio line head could be scaled up to 32 with 1 DRAM to control. So 1 DRAM can link to 32 remote radio line head, and we're totally around 10 gigabit per second from the DRAM can support. And furthermore, we also conduct some EMF measurement and modeling. So EMF is for the measure the radio image and for the millimeter wave and also the VOC. So this is a result from modeling. So this is the same floor plan for the BI lab we are using, and we are doing the test measurement campaign. So modeling the 4 millimeter wave, each individual millimeter wave will have a 20 dB watt, 20 dB milliwatt power. So you will estimate the whole rate coverage. However, not for the real measurement, for one millimeter wave transmitter, we can have mostly the not over the threshold, so the screen. And also the VOC, we don't have any power or radio image from the VOC link. Okay, so this is the measurement results. Now we can have a video to show the whole measurement campaign. We
Start it from the beginning, Yui. Start it from the beginning.
Okay.
Where's the audio? The audio's not there.
Can you hear me?
No, the audio's not there. My audio's not there. You need to increase the audio.
Can you
The
hear
audio. Go to the audio, the speaker at the bottom, and increase it. The audio. Increase the audio.
Can you hear?
No, we can't hear it. Can you go to the speaker and increase the audio on YouTube? On YouTube. No, it's not. It's not doing it.
Yeah, I think you have to just show your screen and you selected show the computer audio, and then we can have the audio directly from the Zoom.
Wait, yeah.
Yeah, I suggest you to you show your screen in Zoom, and when you do that, yeah, you just recode it. Because now I think you just stop show the screen in your Zoom and you do it. And on the left bottom of the windows in the Zoom, you can see authorize to show the computer audio.
Yeah.
And then it will be okay.
These visitors come to see. Yeah, okay, go from the beginning. From the beginning. Demonstration, meaning testing, certification, and standards for organisations in the UK and abroad. The Innovation Park at what open to the public and has welcomed over 2,000 visitors, including guests from the construction industry, local authorities, government, academia, school groups, and international leaders. These visitors come to see the innovations in building technologies demonstration on the BRI Innovation Park. The increased use of wireless local area network communications in buildings is causing congestion and interference, whilst modern building materials are restricting the propagation of radio frequency waves within them. Therefore, building owners have been increasingly turning to the deployment of cellular home networks in their buildings because they operate in licensed spectrum and can avoid interference and congestion. The Innovation Park features full-scale demonstration buildings that have been developed by industry partners. These buildings display innovative design, materials and technologies which combine to address the development challenges facing regions across the world. Technology, demonstration, research, testing, training and dissemination are key activities which underpin the operation and development of the Innovation Park, making this the ideal place to demonstrate the Internet of Radio Light system in a home scenario in its famous integer house, which has been showcasing new home technology for over 20 years. The integer house was also built with a variety of intelligent home automation technologies and advanced communication technologies, such as a telephone service distributed via local building exchange, digital satellite and terrestrial television, web TV and closed circuit television. The Internet of Radio Light project develops a safer, more secure, customizable and intelligent in-building network using millimeter wave and visible light communications. The conceived solution reliably delivers increased throughput greater than 10 gigabits per second, from access points pervasively located within buildings. It does so whilst minimizing interference and electromagnetic exposure and providing location accuracy of less than 10 centimeters at the same time. Here we see two project researchers, Ben and Karim, working in the house measuring performance of the 5G indoor system.
I'm on a conference call at the moment. Can you come?
So, for example, distribution of a 4K TV services can be provided throughout a home. Here you see video streaming to a 4K TV over a 5G VLC link being presented by two of the project researchers, Yui and John. When the 5G VLC signal from the communication LED is blocked, the TV stops playing. And when the 5G VLC signal no longer blocked, the TV resumes the streaming audio-video service. 5G remote radio lightheads are pervasively located in 10 gigabit per second optically networked home, which distributes a 5G compliant multi-component carrier VLC and millimeter wave signal to each room from communication LEDs and millimeter wave antennas. A network home consists of an open-stack, multi-access edge computing server, a Layer 2 processor, a distributed radio access network providing a fully 5G compatible radio communications signal within Ethernet packets, using a 10 gigabit per second Ethernet ring network, to one remote radio lighthead controller per room, and its 4 remote radio lightheads in a parallel processing pipeline. The multi-access edge computing server consists of a software-defined network and a network function virtualization system, which hosts virtual network functions that are used to provide network services. A security virtual network function sniffs packets to ascertain denial of service and rogue transmitter attacks. Local database virtual network function stores distant estimation data from the VLC received signal strength and the millimeter wave time difference of arrival measurements. The location server virtual network function processes this data to estimate the location of users in room environments. The multi-source streaming virtual network function transmits video streaming packets both through the 5G RAN and a lower resolution video through the Wi-Fi network to ensure service continuity. A load balancing virtual network function distributes load equally between the 5G RAN and the wireless LAN network. A 5G home network is able to stream 4K TV, 360-degree and conference call video, and support interactive multiplayer gaming. It is able to support location-based data access applications on smartphones or augmented reality headsets. Here you see video streaming to a 4K TV over a 5G VLC link being presented by Yui and John with and without the presence of illumination LEDs. As you can see, the communication LED's performance is unhindered by the illumination LEDs since video continues to be streamed even when the illumination LEDs have been turned on. The test receiver records 5G received signal strengths QAM constellation diagram, mean and probability distribution of the error vector magnitude, the error vector magnitude evolution with time, the block error rate and throughput for the physical downlink shared channel, the physical broadcast channel, and the physical downlink control channels. Here you can see the millimeter wave recording being taken at tabletop height 0.7 meters, and the performance of the received physical downlink shared channel signal being recorded by Karim, who is one of our researchers. Taking VLC measurements requires positioning the photodiode receiver on a grid, angling it towards a communication LED transmitter, and measuring performance on the test receiver. A 2-degree of freedom gimbal is used to rotate the VLC photodiode receiver towards the communication LED in order to maximize the received signal and hold it in a fixed position for measurement. Taking millimeter wave measurements requires choosing transmit angle, positioning the receiver on a grid, angling it towards the transmitter, and measuring performance on the test receiver. The 2 degree of freedom gimbal was enhanced to be able to do this autonomously. Results from VLC measurements show that the coverage has a diameter of 1 meter and a maximum propagation distance of 2 meters. Angling the receive LED improves the quality of the received signal. Received signal track results have also been used to locate positions with a minimum location error of 3.5 centimeters and 80% of all location measurement errors of less than 10 centimeters. Results from millimeter wave 64 QAM transmissions have shown that for a transmit antenna pointing vertically down, the coverage area has a diameter of around 2 meters at ground level, with improved performance for measurements taken at tabletop level, 0.7 meters above ground, and with improved performance when the receiver is rotated towards the transmitter. Pointing the transmit antenna 30 degrees from the vertical, the coverage area can be better than 2 meters by 1.6 meters. The performance of the millimeter wave system slightly varied from one day to the next, and so is dependent on external factors which could not be identified. This project demonstrator has shown the viability of a 5G network home with just 4 millimeter wave radio heads required to provide sufficient coverage and location services for a family-sized sitting room. It has shown that VLC technology is a good personal area network solution, but requires its propagation distance and coverage areas to increase by a factor of 2 to make it commercially viable.
That's it.
Thank you. So we have seen now the video. I would like to basically now ask for any further questions. You know, I mean, there was the presentation by Yui, there was the video. We have now time for discussion. Hello?
Yes, we're all here.
So here,
Yeah.
it's sharing from ISEP. I think it's not for question. More or less, I want to complete some information concerning the visible light positioning part. And okay, I think everyone knows this is a very special period. That is why we cannot be UK to complete the visible light positioning test demonstration. But I think something is so interesting, like with this not so big area, we can get a very high position accuracy. And based on the PSO AI algorithm, we can make the enhanced position accuracy less than 10 centimeter. And that is also very important for the future. That like the question some people ask in the morning. So how we can make the switch between the millimeter wave and the VLC? Because the accurate position error, it helps us to make the channel estimation is more accurate, and it could be help us to estimate power consumption, and potentially it should be very important point for the future and for the power efficiency design, especially with the multi antenna and the hybrid VLC millimeter wave system design. Yeah, so that's something we would like to complete based on the video that we can all see here, the location demonstration part here. Yeah.
Yes, Sun, you came up with a very innovative idea, which unfortunately we haven't properly presented in these slides, of how we took measurements on a grid.
Oh yeah, but
and how you then took those measurements,
yeah,
all of them, all 64 whatever of them.
So definitely,
to locate the anchor communication LED positions?
We can completely ignore the problem, the angle, because when the people hold the UE, there's always some error on the angle, like the photodiode to the. So, and with the algorithm, we try to regulate this issue. So normally we can do that. We totally believe that we can do it online. Okay, so that means when the UE gets the power ratio, and we need to implement the algorithm on our location server that is already ready here in BRE. So only thing we need to do, so we have to be here, we install our algorithm, the Python program in the location server, and we make it integration test. Normally it can be done. Unfortunately, we cannot put all the job for our college from the Brunel University, because you can see here, it's almost only our students and the technicians, scientific people work on the demonstration building. It's too hard for them. So that is why we decided they make the data collection, the received lighting power and send to us. We do it in our server here. And so that is why we can, that is half online part. Okay, we can just do it currently, the calculation is offline. But we believe, and in the near future, okay, if the situation change, we can totally to realize it quickly in our location server.
Yes, yeah. But what you did was very clever. What you did, we gave you the measurements, all of the measurements.
Yeah.
And then your students created an AI algorithm to search for the locations of the anchor LEDs that would minimize the errors of all the measurements that we took. And that's why you got such good results with the minimum error of, what was it, 0.5 centimeters, an average error of, can't remember now, 3.5 centimeters, but 80% all below, all below 10 centimeters.
Yeah, all below the 11.
Yeah, averaging 5 centimeters, and the minimum is 0.5 centimeters error.
5 centimeters, okay.
Yeah.
And so same principle, that can be extended to results can be extended to a VLC system which has greater propagation distance and wider propagation angle to provide similar level of results. So that part of it looks very promising, right?
That's to be honest, it's not like this kind of result we're waiting for, but so we are so excited to get this kind of result. It's really good. And by the way, we don't really to make a special configuration and in BRE because we are not here. So that means we just ask Ben, like, okay, come on, just give me some test point, the 30 test point, give me the result. Okay, and Ben did really good job. They give us the photodiode receiver, the angle. But to be honest, in our algorithm, we just okay, we don't care it. We just use the received lighting power to make the calculation. Even that, we can get the very good result. That is so nice.
And also, yeah, we don't change the waveform, so they are using existing 5G new video waveform.
Yeah.
So we are doing the positioning and also data transmission at the same time. So at the same time, we still receive the streaming data, the video streaming data. So display at the same time we do the measurement for the location.
So that is something we are just to complete the question. The morning people ask, so why we don't use the frames, the slot for the PRS? I think. And it's totally possible. Okay, it's just only we can move our the positioning packet information on the BRE, and we can complete it, integrate it our VLC location protocol in 5G position protocol in the standard. That is completely possible to do that. Yeah.
And the other thing I'd like to point out that. When you showed the millimeter wave results, Yui, you showed that on one side, the results weren't quite as good as on the other side. That we worked out was due to the glass doors for the patio reflecting the millimeter wave signal, and we proved it because when we drew the curtains, okay, it improved the reception, and then we drew back again. The reception wasn't as good. It went back to what it was before. So the amount of smooth reflective surfaces around a room plays an influence in the performance of the received signal.
Yeah, this also gives a hint for the millimeter wave. For the receiver, normally we need to use like a beam, like a antenna array to do the beam forming. So to attract the beam pattern for the arrival angle. So instead of use one antenna, we have to use the antenna array to steer the beam, digital beam. So to tracking. So if you're changing, for example, if our environment is changing, you may have a different reflection parameter.
We did have some measurements also for the electromagnetic radiation that was measured by the building research establishment, but we didn't quite have enough time to squeeze them into the presentations. But they do now feature in the measurement report that we are compiling of all the measurement results.
Yeah, the power EMF is much lower than the regulation. So the regulation for indoor regulations, they have certain power level defined by the Ofcom, but according to BRE measurement, the EMF much lower for millimeter wave and also for VOC.
Yeah, given the current performance, it's much lower than what's regulated, what the regulation maximum is.
Good. If I may use this opportunity now, gentlemen, to ask our audience whether they have any particular questions that was unanswered, or they just have another question that just occurred to them. I mean, this is the time now to come forward with any, any questions. I mean, this is our discussion time. We still have quite some time, right? Even if we count in some time to switch over to the roundtable discussion. Please, I mean, if there is any question, I mean, we are here. I mean, a number of experts from the project are here to answer any such question. Earlier, I maybe I was a bit strong-handed. I had to ask you to post those questions in the chat, because we wanted to make sure that the project presentations can take place and we are not slipping with the agenda. But this is now the time to, if you have any questions, to ask those questions.
What I would like to say is that without the Viavi user test terminal, we wouldn't have been able to take any of these performance measurements, and so that was crucial to the measurement campaign in order to attain these results that we were able to present to you. Also, each graph that you saw it took 1 week. So every graph that you're looking at, it took 1 week to build the whole system up, right? And then it took each graph 1 week to produce. So there's quite a lot of work there.
Yeah, each graph represents roughly 20 to 30 points measurement.
Yeah, 1 week work. Because not only did we have to create the graph, take the measurements, we had to plot the points on the ground, and then work out what was going on, make modifications by creating the gimbal, and so on. And then the whole thing took each time we took a new set of measurements, we had a new set of problems, and we had to, and the whole thing took 1 week. You see. So that's why the whole 3 months. It took 3 months to to do all these measurements, and it still goes on because we feel that we can improve the VLC again with an enhanced system from Oledcomm, and we're currently also debugging the uplink millimeter wave system as well, in the hope that we will be able to produce a return channel as well. It's not so easy. But it's a reference system that can live in a neutral location like the building research establishment, and we can build on it to test other improvements to the VLC and millimeter wave transmitter and receiver systems, because we've got 5G, all 5G, of course.
Good. I mean, either we are very clear or our audience is running out of questions.
It was also quite interesting. Ben, maybe you want to talk a little bit about the requirements for virtual reality location estimation in order to position. But Ben, are you there, Ben? No, he shot off. Oh, no, he shot off. Yeah, okay. So, but we're getting accuracies of around, less than 10 centimeters, but that needs to be improved by a factor of 100, really, if it's going to be used for virtual reality headset to position the virtual reality headset and align it with its virtual environment. It needs to be done to around less than 1 millimeter accuracy, and so there's still a lot more work that needs to be done for a totally, if you like, tetherless, free virtual reality and augmented reality headsets to align them properly with their virtual reality information, you see. So that's still a challenge, and so this is another step towards that achieving that challenge, so that it can make augmented reality and virtual reality headsets totally tetherless. If Ben was here, he'd be able to talk about it in much more detail than I can, but I'll give you some sort of flavor of what it is. The other great innovation was Robert's wonderful. Robert, tell them how much it costs for an antenna system that's being machined, right? You were telling me around 10,000 euros, right? And how much is your antenna, your PCB-based antenna system would cost in the order of tens of euros. So that's makes the whole system more, if you like, commercially realizable, you see. So that's a great innovation there, I would say.
Yeah, John, you're right. But you can also save more money when you bring an antenna direct to the PCB. But in this case, you lose a lot of bandwidth. You cannot feed the full bandwidth of both 5G bands. This was the goal of the system, that we like to figure out what is the best frequency range. So yeah, you can save more in an antenna when you bring it directly on a PCB, because we use already have PCB, and just this is a console as a result. But the antenna is nice when you like to separate it from the up and down converter.
So what would you need to do, Robert, because we could only use one polarization, one vertical or horizontal polarization. We would need two antennas for one vertical, one horizontal. What would you need to do if you wanted to enhance your system to make it
No,
circular polarized, so that it only has one antenna or access point, right? You see.
No, now we have like the option with the final version of the transceiver. They have always 2 TEAC channels and 2 ERIC channels, and we can use the new dual polarized antennas that are present in the morning. They are now finished. They have a less bandwidth. They're working only with the cheap, as I will say, I have a cheap version and an expensive version. The cheap version is the direct soldering of the coaxial cable to the PCB. Then the antenna have a bandwidth of 4 gigahertz. It's dual polarized. It's not so cheap than another one because you need 2 cables, and the 30 gigahertz cables are much more expensive than the PCB and the antenna body. You can use also on a PCB like a SMP connector and use a SMP to SMA, or but it's not SMA, it's K connector to connect the antennas. But the connectors for the antennas is much more expensive since the other things. Also since the PCB and the one for the antennas, the most expensive one is to bring from the inside of the lamp the PCB, as the up and down converter, the signal outside of the lamp body, and this cables cost mostly the most money for the antenna. I don't know how we can deal. We can always save money when we direct sold the coaxial cable with some magic networks on a PCB. You can save 30, 45, 50 U, depends on the frequency range, but you also limited the bandwidth. It's a trade-off. But for the final demonstration, when we have the chance to set up it, I would like to show that it's also possible with the dual pole system, and then we can do whatever we like. We can send both polarization the same signal. We can use 90-degree phase shifting to make a circular polarization. We can think about to use polarization MIMO to increase the data rate. We have a lot of possibilities in this project with the up and down converters.
Yes, that's excellent. And then, of course, the VLC. Bastien, what's your opinion on how we could improve the omnidirectional capability of the photodiode receiver? Because originally we were going to have a lens to do it, but we found that that wasn't sufficient. So this is why we resorted to angling. What do you think of my idea of having like a fly's eye receiver? Is it too wacky, or what's your opinion? Coming from a manufacturer of these devices.
So I would say there are several things to improve let's say the coverage of light communication system. First, basically the coverage depends on the signal to noise ratio. So the larger the SNR, the better the communication. So the goal is to optimize at any point of the receiver plane this SNR. The first way to do it is to work on a transmitter and to improve the performance of the transmitter, especially when we are using modulation like OFDM. We better have a good linearity of the transmitter so that the OFDM signal is perfectly transmitted. Then on the receiver side, as you said, we can work on the optics, which is one part, and the other part is to work on the receiver, the sensitive component itself. And as I said in the talk this morning, there are mainly 3 parameters, which are the sensitivity, that is the capacity to turn photon into current. And in order to improve this sensitivity, well, the best is probably to use components with high sensitivity, that is avalanche photodiodes. These avalanche photodiodes, they have sensitivity in the range of several tens of amps per watt, which is really high, especially compared to pin photodiodes, which are usually in the less than 1 amp per watt, basically. But also, as I said this morning, these APDs, they have a pretty large cost. So earlier today, someone asked, how can I have this fitting into my laptop? Well, first, we have the technical points. We want something that is performant, that can be integrated. But then we also have the economical point, like an economical problem. And APD, although they provide very good performance, from the purely technical point of view, they are still, from the economic point of view, very expensive and quite hard to use and to implement in such a constrained space as a smartphone. So one way to improve the performance is to work directly on these sensitive components and to have manufacturers such as, I don't know, Hamamatsu or whatever, Osram or other suppliers like that, improving their the performance of the receivers directly. And we've seen, for example, that the automotive industry has pushed these suppliers to develop new components, especially because the LiDAR is now being more and more used. So hopefully something similar will happen with light communication. And then there is the sensitive area, but it's kind of like the photosensitivity. And finally, there's the optical gain. And this led me to the optical part that you mentioned, John. There's still a lot to do, to be honest, on this part. Maybe, yes, maybe the kind of system that you propose to use could be a good idea, and it surely should be tested in order to check what is the improvement. But there is definitely one challenge, which is that basically we want to improve the gain of this optical system in order to improve the optical signal collected, so the signal to noise ratio. But the gain increases when the size of the optical system also increases. So at some point there's going to be a problem, because again, if we want to integrate a light communication receiver into a laptop, we cannot have this massive lens. So one way is maybe to use freeform optics, and there's been some work on that at Oledcomm, but not only. Quite a lot of academic work has been published on the topic. So freeform optic is, more generally speaking, a rather hot topic in optics, and the idea is to use systems that do not have any more an axis of rotation, but that are really freeform. It's in the name, and it's rather promising to have, let's say, a fully or almost fully customizable gain. So these are several leads to follow in order to improve the performance of light communication, and to also have it integrated into smartphones, laptops, or devices in general.
Well, we got a comment from Alex Adolf, and he's suggesting, his comment was Fly's Eye points to Fresnel lens configuration plus grid sensor.
Yeah, instead of the Fly's Eye, I mean the Fresnel lens configuration plus grid sensor.
Okay.
Yeah, I mean then indeed. Thanks. I don't know whether it's a real name or not, but anyway, good.
I'd like to continue with the conversation with asking Israel. I mean, Israel, I'm very excited about your. You mentioned, I'm not sure if everybody noticed, that you can have more than one 10 gigabit per second ring on your system, up to 8 of them, to make the whole thing 80 gigabit per second. How are we going to keep up with you? Because we had all sorts of problems in the project finding a layer 2 processor that could go fast enough to support your voracious consumption of Ethernet packets. So can you say a few words about that, Israel?
Yes, the concept is that we designed this DRAM to be able to support up to, let's say, 64, or you say 32, it depends on how many beams in which RRH or remote radio light head. So by doing via this fiber ring, you can increase the capacity of the whole network by adding more and more remote radio heads. Actually, this ring is not yet adopted by the ORAN organization, but we believe it's a great idea to cover highways or buildings or stadiums and we will try to promote this idea of the ring. Otherwise, right now they are proposing to connect in a star architecture, which is it's also good but more limiting. That's the idea. I don't know. I think Zion is also in the call. Maybe he wants to add anything. Okay.
I just was away and came back. What was the question?
Which was that you have a single 10 gigahertz ring, but Israel did mention that this can be increased up to 8 to make it a total 80 gigabit per second multi-ring system. So that's correct. That's very exciting.
Yes, correct. We have this kind of 8 interfaces, but basically we are using 2 of them backward, where the core and 6 of them can be for the frontal.
But how are we going to find a layer 2 processor to keep up with you? We barely managed to keep up with you in this project. And in fact, it kind of restricted us, didn't it, really?
I don't think so. We did what we promised. The major problem that we faced in this project was the lack of L2 interface, L2, L3 interface,
yes,
according to standard. So we put a lot of effort to try to emulate this, and the video and everything, which was not supposed to be our part, but we did it in order just to make progress in our whole program. So, and unfortunately, in the middle of the way, you are right, we found in the company a need to convert some of our front all toward the ORAN interface. I think Viavi doing the same. So, but now we have uplink. We're waiting for you again. So hopefully we manage that for the next project to run the whole thing together.
Yes.
Okay. John, I was just wondering whether you whether you wanted to say a few words about that. I mean, as part of the IEEE BMSB, so the main conference itself, there are, I think, a range of talks or contributions from IoRL. I don't know whether you wanted to say a few words about that.
I'm just about to get them ready, if you don't mind.
Right.
Right. I'm trying to multitask here.
Yes. So maybe I should say something, right? I mean, I know that the conference itself, it's not free of charge, right? Unlike the workshop today. But we are rather proud that we were quite successful. We submitted papers to the conference, and a good number of them has been accepted and will be presented in the coming days or during the course of the conference itself. So, I mean, as you know, part of the closing of the workshop, I wanted to point this out, and John is probably getting ready with a slide.
Yeah, I'm trying to, to
present
this.
I'm
missing one. I'm thinking I'm missing in Noir's paper, but I'll show you what I've got.
Right. And then, as I said, I mean, we're slowly wrapping up the session here, because I will kind of, you know, I mean, step down, because the roundtable discussion that we were you know, pointing out earlier, this is going to be happening, as I said, it's going to be a hybrid discussion, so partly physical in ISSY, and the language of that one will be French, and the moderation and everything is then done by the local people. So, yeah, okay, so here is the something that John wanted to share. Yeah, I mean, okay.
Here they are.
So yeah, so well, it would have been nice to say that in which time or which.
Yeah, no, you got
okay.
me by surprise. There is another paper by Noir.
Yeah. But as you can see, I mean, we were rather successful. We got something like 6 papers in the conference, and I mean, if you have the chance, or if you are planning to attend the, please watch out for those papers. I mean, they might shed further details to some of the work that we've done in the IoRL project. Into some very specific aspects.
I know. So, Sun, did you publish? Did you present? Are you presenting a paper, Sun, in this conference as well?
Yes, yes.
Oh, there's 7 then. There's 7. I didn't. Don't have.
We can talk about later, maybe.
Yeah, I don't have the that one.
I mean, right. So just want to point out to people that if they have the time and the opportunity, then there will be further results, details being presented. And yeah, I mean, maybe what I could say that I will now take the opportunity to actually post in the chat channel the links to this roundtable. So people who want to transfer there to this this French language discussion of the local stakeholders. This is another bridge or another Zoom conference room or meeting room, and I just posted it there, so you are all welcome there. If you wish to follow the discussion, as I said, although it's going to be in French, but we will provide, or the local organizer, they will provide a translation presented in subtitles. So I think even those who are not speaking French, but they can also follow this discussion. Right. I don't know whether there is any last questions that we can discuss here and now before really closing this. I mean, I'd
like to express my thanks to IEEE Broadcast Society for, as I said earlier, for first of all being a platform from which Sun, Yui, Jian, and I got together to all those years ago to come and discuss what possible innovations we could come up with. It was appealing enough to be funded by the European Union, and then also to be supportive enough and flexible enough to be to help us present our IoRL workshop as a sort of like a tutorial session before the actual conference itself. And with the advent of COVID, to be flexible enough to be able to come up with this really innovative approach to having conferences over Zoom links. And I think we got so many more people coming to the workshop that we would normally have had, and it has been a far more, I would say, rewarding day as a consequence.
Yeah, thanks, John. Yes, indeed. I mean, we haven't emphasized this aspect of it, but indeed the project was hit quite badly by the pandemic, because it really took us at the point when we were still in the middle of our integration work. In front of us, demonstrations, and I mean, you have seen the nature or the type of work that the subject, right? Let's say, right? I mean, you have seen how it looked like. I mean, you can imagine that how difficult it was to overcome the situation and still manage to complete the integration and get and install the system at least in one location, even if we did not manage to then start shipping it around and doing on-site or in situ demonstrations elsewhere. Good. Right. I mean, the reason why I'm maybe a bit anticipating the wrap up here is that I expect that maybe this transfer to the other meeting room, it might take some time. Maybe I'm overcautious.
Have we come to the end? Are we another half? Is it 4:30? That
4:30 is starting the one. So we
yeah.
have
So there's another 25 minutes, isn't there?
We have another 20 minutes to go, John. But I mean, I haven't seen any questions from the floor. I'm very happy if there is still some more. To take any of those questions. I mean,
I'd like to ask because Harilos, because toward the end of the project we did have some activity to make a slicer so that we could slice the bandwidth, and the NCSRD people do that. We didn't present that in the in this workshop, but perhaps Harilos, you can say a few words about the slicer that you had built.
Well, unfortunately, the slicing approach has been applied based on other projects,
yes,
and has yet been extended to the IoRL project.
Yes.
Instead, what we did is that we presented the very main let's say, design of this of a potential slicing mechanism could be applied in IoRL.
Yes.
Well, that's all, which is presented in the latest deliverable of work packet 3. We also our focus lately was to expand and perfectize the access point assignment problem. So that's the current status.
Maybe we should also then tell to our audience that yeah, I mean the project is now really approaching its end. We have 1 more month actually to go, so you should expect all the public documents, deliverables to appear on the project website shortly, in the 1-2 months time, and yeah, I mean hopefully containing a lot more insight for that, so we can yeah, satisfy your interests to more detail. And as I said, but even more immediately, I mean, there will be a few more talks within the BMSB
Adam, where is the video of the workshop going to be placed?
Sorry,
you know,
I mean, we haven't discussed. Yeah, no, sorry, right. So the recording of today, right? Yeah. This was asked, this question, and we haven't really discussed it. But I mean, if we can, we will put it on the IoRL YouTube channel. I mean, we take the opportunity that, I mean, so whoever registered for the workshop, we will contact them to wrap up and let's say to close this interaction in the following way. We will release the presentations in a PDF format. And we will also then, and of course, give pointer to everyone who was here on the call today. We will also release the recording. As I said, we haven't thought it completely through, but if it's possible, or more than likely, we will use the IoRL YouTube channel, putting up the workshop recording there. And yeah, but we will notify you about these final steps, let's say, if there are any further questions, I mean, you are more than welcome to contact the management teams through the IoRL contact email address provided on the project website, and so on and so forth.
Yeah,
this is also there. I mean, yeah, I mean, if there is still, yeah, I'm sure that there might be still open questions to many people.
Would we have done anything differently in the project, Adam, if we had our time again? That's always a question to answer.
Well, sure. I mean, John.
What would that have been?
To be honest, John, I don't know. I mean, this is supposed to be now a scientific workshop, so I mean, I'm not sure that I want to go into some organizational issues or some other stuff.
No, from a technical point of view.
But I would.
I mean, from a technical point of view, I think maybe if we had chosen infrared, we would have got better, perhaps, performance from the visible light rather than the visible light system. So that might have given a slightly better performance. Well, quite a considerable better performance, because that transpired. The performance of infrared systems transpired after the end of after the beginning of the project. So by the time we'd started, we were already committed to a visible light communications solution.
I think this speculation now is a little bit. I mean, yes, I mean, we can elaborate quite a lot around it. I mean, yeah. From my perspective, and as I was answering some earlier questions, the visible light communication choice was a very good choice and a very important choice. We made some essential tests that are still groundbreaking, and this was all thanks to IoRL. That those tests were done, and this is still far ahead of the thinking and the progress within the 5G standardization, and I think we have a good chance to be some sort of a reference or to contribute there, or they could benefit from the tests and that were done in IoRL on putting 5G new radio on the visible light channel. As said, in the future works of deciding on the numerology, the waveform for the higher frequencies, which discussion is kind of only starting now. So this is in that sense, I think that was definitely a good choice, and it's still a very valid thing what we've done there. Coming back to the infrared and Li-Fi, I mean, as it happens, and both John and me know it very well, there are various ways of integrating the different technologies. Any sort of light-based communication and millimeter wave or radio, right? And 5G permits this integration or foresees it even more openly in embracing non-3GPP, so non-5G access technologies, and you can do that, and this is possible through the so-called non-3GPP interworking function. But of course, this is an entirely different sort of thing, and this is possible. It is being done and experimented as we speak in some other project. But this is good. It's all and good because, I mean, we are IoRL and we complement other projects, or they complement what we have done here. Maybe the path is more immediate or more straightforward, as I said, but there are always trade-offs, and we know that. And well, I mean, I don't know whether we can already say a few words about it, but there is an ongoing work within the 5G PPP, public-private partnership, and as part of the technology board of the 5G PPP, where IoRL teamed up with a few other 5G PPP projects to create a white paper, a 5G PPP white paper on indoor communications. This is an ongoing work. We hope that we can complete this work pretty soon. We have received a lot of good input. John and me are part of the editing team of that white paper. We have received also tried to capture a lot of input from the IoRL project itself. But there are other projects that are addressing indoor, more specifically focusing on Industry 4.0 or industry or manufacturing type of application scenarios, having specific focus on location. So we felt that there is a critical amount of interest or input that is available already, and we started this process, and we hope that this will come and bring fruit pretty soon. And please watch out. I mean, we are in the process of defining or elaborating this white paper.
So in retrospect, actually, we originally had envisaged the millimeter wave and the visible light systems to sort of sit side by side, but because the millimeter wave systems can have bandwidths up to 400 megahertz, whereas the visible light at a push can get to 20 megahertz bandwidth. We had a problem with the remote radio light head controller not being able to provide both without considerable sort of FPGA processing power. So in the end, our solution was sort of a system that we were able to compromise both coexisting at the same time. So it may point towards a system where the millimeter wave part of the system would be provided by a 5G type indoor network, whereas the visible light part of it could use some other technology, because of the fact that it's not so easy to provide a remote radio light head controller that will provide for both without being a considerable expense on the FPGA chipset.
But not to mention, John, actually an important aspect that some of these, the standardization 3GPP or the mindset there is to look for the higher bandwidth. So the assumption is that the minimum channel spacing is something like 50 megahertz, or in a very restricted case, maybe going down below that. And some of these thinking is only starting actually now. I'm sort of aware of some discussions, partly coming from the satellite community, where bandwidth is a lot more costly or precious thing, and therefore so some of these standardization steps are still in front of us, right? So and you're right, and there is also a technical challenge, how to accommodate and combine let's say significantly different bandwidths on the same platform. I mean, this is something we also need to still think about or consider whether it is possible and whether it is desirable. But still, I mean, I think some of the, you know, as I said, some of the outcomes were very valuable, and in many ways they are still ahead of their time. So let's say some of these questions are still to be answered within the standardization. These are still open, and yeah, I think how should I say, the results of IoRL are in that sense are still relevant there. And not to forget, I mean, we had through this putting the 5G new radio on the visible light channel, we had a completely uniform system with a unified handling and control.
Totally 5G compliant.
And resource allocation and everything. Exactly. So I mean that's a great advantage in my view. Whether we can reconcile some of those considerable challenges that you mentioned, I mean that's another point. Good. Yeah. Let me. I think
we've had a good discussion, although it has been between ourselves in a sort of reflective mode rather than it being coming from the, because I can understand our visitors not being familiar with the issues that we've confronted, but I hope this discussion has given our visitors some sort of insight into what sort of issues confronted us and how we had to come up with decisions to make the project work, as it were. You see what I'm saying? So that ultimately.
Good. Okay, I think with that we would like to thank very much our audience for their patience, their time, their interesting questions, digging into certain aspects. I have seen that there was also some further follow up on the point regarding the Fresnel lenses and grid sensors and whatever. I think this is all very nice. As I said, I mean, we are going to put up the slides on our website, and we will have some final closing communications to you with pointers to the slides and also about the recording that was made today. I would like to hand over now to Zhang from ISEP, because I mean now we are, I think, really at the moment, and we should transfer to the other meeting room, right? I mean, if you check in the chat channel, I have sent you the link to this kind of follow up or the roundtable discussion, which is in a different Zoom meeting room. And as I said again, as I said already, let me just repeat, this other discussion will be a roundtable discussion. It will be kind of broadcasted from ISSY. There will be some people on site. It's going to be a discussion of the local stakeholders. The discussion will take place in French. And however, we try to provide you a translation in subtitles in English. And yeah, I mean, that's it from my side. I mean, as I said, I will step down from now because my French is not good enough. So the rest will be handled by our local host from ISEP and IssyMedia. And I would like to thank all the speakers for their time, also for their comments, and thank the audience for your time and interesting questions.
Okay, thank you, Adam. Could you help me? I just show you some picture, and we are here to try to arrange the meeting here. I don't know, could you? So basically the roundtable is based on we talk about application. It's a few technical side we are talking about. It's just to think about when our 5G arrive, how we apply it. And in IoRL project, we are thinking the different scenario, like you see the smart home, and also for the museum scenario. That is something we're talking here. So, and please join us. Okay, so, and the link is Adam showed already in the chat. Okay. So see you in another meeting room. Okay, thank you, Adam.
Thanks everybody.
Thank you. Bye-bye.
Bye-bye.
Bye.
Thank you. Bye-bye.
Thank you. Bye-bye.
Yeah, just take care and you know, copy the link. I will stay on this Zoom room for a little longer, right? Just to make sure that people can, you know, still join here or come back here or whatever. You know, copy from the chat the link to the other meeting room, and you know, let's see you there in a couple of minutes, right? The other discussion will start at 16:30. And myself, I'm also very keen and interested to listen what will be happening there. So the follow-up meeting is, the link to the follow-up meeting is in the chat. You might need to scroll up a little bit. There is a link, and yeah, and we will end this conference now in the next minute. Thank you, everybody.